In today's video lecture, we're going to start the packet of notes dealing with frequency response. Frequency response is closely tied to sinusoidal steady-state analysis that we covered in the last packet of notes, but it goes a step further. If you recall, in sinusoidal steady-state analysis, we looked at the response of a circuit to an input of a given frequency. So the input was a sinusoidal of a certain frequency. The output, whether it be some voltage or current, was at the same frequency as the input, but the amplitude and the phase could be different. And sinusoidal steady-state analysis gave us techniques for evaluating what the output voltage or current would be. Frequency response goes a step further. Rather than looking at the input at a single frequency, we're going to look at the input over a range of frequencies and try to get a picture, either mathematically or with a physical plot or both, get a picture of how the circuit responds to a variety of input frequencies. And this is what frequency response is. So you do want to briefly read in your book sections 14.1 through 14.5. I do want to point out that you really only need to look at this briefly. The book goes into much more detail than we will in this course. Follow-up courses in electrical engineering talk about frequency response in much more detail. As a brief introduction to what we're going to look at on the following pages, let's consider a very simple RC circuit. So imagine a circuit where you have an input signal Vin of t, a resistor R, a capacitor C, and you're interested in the voltage across the capacitor. Let's call that the output signal. So up until now, we've looked at everything in what we call the time domain. So plotting wise, in the time domain, your x-axis is time, your y-axis is whatever you're looking for, in this case V out. Suppose, for example, the input was a unit step function turning off at time 0. So maybe your input looked like that. The corresponding output would be what? Well, you'd be in DC steady state here, and then once the input turns off, the capacitor would start discharging and eventually go to 0. Or maybe you have a situation where the input is a unit step function turning on at time 0. If that was your input, we saw that the output voltage would start at 0 and it would start rising exponentially and eventually get up to a set value. Or in the last packet of notes, we saw that if the input was a sinusoid of a certain frequency, the output would be a sinusoid of the same frequency, but with a different amplitude and a different phase. So the corresponding output might look something like this. So that's all time domain. In this section of notes, we're going to look in the frequency domain. And we're going to see that the plots that we have show information in a very different way. First off, the x-axis rather than time is going to be frequency, either measured in hertz or radians per second. Second thing, we're going to see that we're going to measure not V out as a function of time, but we're going to measure the magnitude of V out. And the plot's going to look something like this typically. This is a typical frequency response plot, and these would be frequencies 10, 100, 1,000, 10,000, 100,000. Notice these frequencies are on a log scale. We'll talk about that in the subsequent pages. But anyway, this is a fundamental difference between the frequency domain and time domain. In the time domain, you're looking at the output as a function of time. In the frequency domain, you're looking at the output as a function of frequency. It gives you information in a very, very different way. So let's start looking at this in detail. So in the last packet of notes, we did sinusoidal steady state analysis where the input was at a single frequency, or in some cases later on in the packet of notes, we might have had 2 or 3 or 4 different frequency inputs and calculated the output. But very often we are not interested in finding the output at one particular frequency. Instead, we want to see how the circuit responds to a range of input frequencies. We call this frequency domain analysis, or the frequency response. So the idea here is we still have an RLC circuit of arbitrary complexity. Now the input is going to be a sinusoid, where rather than varying the amplitude or the phase, we're going to vary the frequency of operation. What we're going to see is that when you vary the frequency of the input, the frequency of the output is going to vary, because the output frequency is always the same frequency as the input. But what we're also going to see is that the amplitude of the output and the phase of the output vary as the frequency of the input changes. And this is what we call frequency response or frequency domain analysis. And it's going to give us an overall picture of how the circuit behaves at a variety of frequencies. So how can you measure the frequency response? Well, there are a couple ways you can do this. If you recall, in Lab 7, we did this with the Baxendale tone control circuit. What we did is we measured the frequency response experimentally. So what we did is we swept the input signal across a range of frequencies, and we measured the output signal for each of these frequencies, and you could tabulate that in a table to see the relationship between the input frequency and the output amplitude and phase. For example, you might have a table that looks like this. You'd have your frequency, you'd have your magnitude of your input signal, you would have your magnitude of your output signal, you would have your phase of your input signal, and also the phase of the output signal. So for example, we might have frequencies of 0, 100 radian per second, 200, 300, 400. And we might have the magnitude of the input not changing at all. So keep it all at 5 volts. And let's keep the input phases all at 0 degrees. What we'll see experimentally is that the measured output voltage could change as a function of input frequency. So for example, at DC, the output may still be 5 volts. Maybe at 100 radians per second, it's 4 volts. It might drop down to 1.3 volts at 200 radians per second. And then maybe 0.1 volt and maybe 0.01 volts. Likewise, the phase could change. At DC, well, DC doesn't have phase to begin with, but DC, let's say the phase is 0. And then maybe at 100 radians per second, it's measured to be 40 degrees, then 75 degrees, then 88 degrees, then 90 degrees. And once again, if you think back to Lab 7, you did measurements like this for the Baxendale tone control circuit. Let's illustrate this here with a simple multi-sim simulation. So suppose we have a simple RC circuit, so 2 ohm resistor, 500 microfarad capacitor. We're driving it with a function generator that's set up as a sinusoid, and we're measuring both the input amplitude, that's this yellow signal, and the output amplitude, that is this blue signal down here. So we'll start with a frequency of 20 hertz. So notice the output looks to be the same amplitude of the input, and there's actually a slight phase shift. It's hard to tell because there's not much of a phase shift at all. So now let's see what happens as you increase the frequency of the input signal. So let's turn on the simulation, and now we'll start increasing the frequency of operation. Notice the output frequency tracks the input frequency. And notice you don't really see much of a difference here. You do notice some change in the phase a little bit, but as you start increasing the frequency of the input, eventually what we notice is that the output amplitude is changing. Notice the input amplitude is not changing. The input frequency changes. The output frequency tracks the input frequency, but notice the output amplitude starts dropping. And as you continue to increase in frequency, you notice definitely that the output amplitude is dropping. In other words, the amplitude of the output is a function of the frequency of the input. We can change the time scale here a little bit to make it easier to see again. And once again, as we continue to increase the frequency of the input, notice that not only the frequency of the output changes, but the amplitude of the output changes as well. And this is the frequency response. So you could, if you wanted to, pick a whole bunch of different frequencies, and for each frequency, measure the amplitude of the input, in this case not changing, and the amplitude of the output, which is changing. So this is the first way that you can measure the frequency response. You could do it experimentally. In addition to measuring it experimentally, as we did in lab in this course, you could calculate the frequency response analytically, mathematically. The idea here is you convert every capacitor and inductor to its equivalent impedance, but you leave it as a function of omega, because we're not looking at the output at a particular frequency, we're looking at a range of frequencies, so we want to leave omega as a variable. Then what we could do is come up with an analytical equation to determine the desired output phasor, output voltage, output current, etc. in terms of the input phasor, and then cast the solution as a ratio, output phasor over input phasor. And what we're going to see is this variable omega will remain in the expression. We call this ratio of output phasor to input phasor, we call that a transfer function and give it the designation h of omega. An example of a typical h of omega would be 1,000 over 1,000 plus j omega. What we notice with these transfer functions is that they are functions of omega, and they also, in general, will have some complex numbers associated with them. What we're going to see is that this transfer function equation itself is not terribly useful unless we manipulate it a little bit. What we're going to be creating, and we'll see this in subsequent pages, is what we call the magnitude response. That is the magnitude of this transfer function. This is called a magnitude response. And a phase response, which is going to be the phase of this output function. What we're going to see is that this general transfer function is a complex function, but this magnitude and phase responses are both real functions. And we'll see these on the example on the next page. So in this example, we have a simple RC circuit, and we're asked to determine the frequency domain transfer function of this RC circuit. We could measure it experimentally, as I did in that multi-sim simulation a couple minutes ago, but here we're going to come up with a mathematical equation relating the output phasor to the input phasor. So the first thing we would do is convert everything to the phasor domain. A 2 ohm resistor remains 2 ohms. A 500 microfarad capacitor becomes minus J over omega C. So we get minus J 2000 over omega. And notice we're leaving omega as a variable here. The input we'll call V in phasor. And what we're measuring, this output voltage, we will call V out phasor. From voltage division, we know the V out phasor is what? It's going to be this impedance over this impedance plus this impedance times this voltage. So V out phasor is minus J 2000 over omega over 2 minus J 2000 over omega times V in phasor. So the transfer function is just the ratio of output over input. So H of omega, by definition, is the output phasor over the input phasor. It's just going to be minus J 2000 over omega over 2 minus J 2000 over omega. To make this look a little nicer, let's multiply this by J omega over 2000 all over J omega over 2000. So we're multiplying it by 1. But this turns the numerator into 1. J squared is negative 1, so that negative cancels with the negative that's already there, and we get positive 1. And in the denominator, we get 1 plus J omega over 1000. And once again, we're going to call this our transfer function H of omega. As I mentioned on the previous page, this is a complex function. By complex function, I simply mean when you evaluate it at a particular value of omega, you're going to get a complex number because of that J term in there. This has limited use, so what we want to calculate is two subfunctions, what we call the magnitude response So the magnitude response, which we give the symbol magnitude of H of omega, is the magnitude of the numerator. The magnitude of 1 is just 1. What is the magnitude of 1 plus J omega over 1000? That's the denominator. The magnitude of a complex number is always the square root of the real part squared plus the imaginary part squared. So it's the square root of the real part squared plus the imaginary part squared. The imaginary part is the argument of J. So it's going to be 1 plus omega over 1000 squared. You work that out, you get 1 over the square root of 1 plus omega squared over 10 to the 6th. This is a specific magnitude response for this value of resistor and capacitor. The more general case, if we leave the resistor and capacitor as variables R and C, we would have gotten 1 over the square root of 1 plus omega squared, R squared, C squared. Likewise, we have what we call the phase response. So the phase response, we have the angle of H of omega is equal to the angle of the numerator. The angle of a real number is just 0, so it's going to be 0 degrees, minus the angle of the denominator. The angle of 1 plus J omega over 1000 is inverse tangent of the imaginary over the real. And we need to subtract it, so it's minus inverse tangent of the imaginary over the real, which just happens to be 1. And likewise, the more general case for the phase response here would be minus inverse tangent of omega RC. So we not only have our transfer function, which is a complex function, we have our magnitude response and our phase response, which are both real functions of omega. Okay, so at this point we can calculate analytically H of omega and its two sub-equations, the magnitude response and the phase response. But what physical meaning do these have? What can we do with them? Well, we can do two things with them. The first thing we can do, suppose we want to analyze the circuit at a specific operating frequency, omega naught, 100 radians per second, 200 radians per second, 1000 radians per second. Rather than analyzing the circuit from scratch again, all that we need to do is evaluate our transfer function at the frequency of interest, 100 radians per second, 200 radians per second, and we get a complex number. That complex number tells us how much we need to adjust the amplitude and the phase of the output. In other words, suppose you want to evaluate h of omega at some frequency omega naught. It's going to be some magnitude number at some angle. So for example, maybe you have 5 and an angle of 40 degrees. What this tells us is what we need to multiply the input amplitude by to get the output amplitude. So if the input is V in cosine omega naught t plus phi in, the output magnitude is equal to the input magnitude multiplied by this number here. How about the phase term? The phase term tells us what we need to add to the input phase to get the output phase. So you multiply the input magnitude by the magnitude of the frequency response to get the output magnitude, and you add the input phase and the phase of the frequency response to get the output phase. So you add that to get the output phase. So in other words, this transfer function, if you evaluate it at specific frequencies and express this in polar form, it tells us how much we are transferring information from input to output, how the magnitude is adjusting and how the phase is adjusting. We'll do an example on the next page. The second thing we can do, rather than plug in specific values for omega, we can plot both the magnitude response and the phase response versus omega, and we get what's called frequency response plots. These give us a graphical view of how the circuit changes as a function of input frequency. For example, you've seen these before when you've looked at specs from a speaker. You might have seen something called a frequency response plot. That's exactly what it's telling you, is how that speaker works at different frequencies of an input signal. You also have these frequency response plots in a communication channel to see how a particular communication channel, a fiber optic cable, a coaxial cable, air, any type of communication channel might change the input signal as it goes through the channel. So let's first look at this idea here. So let's go back to the same circuit we had before, and from before, what do we know? We know that the transfer function, h of omega, is 1 over 1 plus j omega over 1000. Now we're asked to find the output for 3 specific inputs. Notice all 3 cases have the same amplitude. Doesn't have to, but in this example it does. All 3 cases have a different frequency of operation. And in this example, all 3 cases have different phases as well. So what you would do is you would start with the first case. Set omega equal to 200 radians per second. So h of omega evaluated at a frequency of 200 radians per second is what? It's 1 over 1 plus j 200 over 1000, or 1 over 1 plus j 0.2. Once again, that is in rectangular coordinates. It's probably more useful to put this in polar coordinates. 0.98 and an angle of minus 11.3 degrees. What this is this is the magnitude of h of omega evaluated at 200 radians per second. And this is the angle or phase of h of omega evaluated at a frequency of 200 radians per second. So what this is telling us is that if the input is at 200 radians per second, this circuit is going to amplify the input by 0.98, and it's going to shift the angle by negative 11.3 degrees. So V out sub 1 of t is going to be what? It's going to be 0.98 times 2, the 2 comes from that, the 0.98 comes from that, times cosine of 200t plus 45 degrees, that comes from that, minus 11.3 degrees, or 1.96 cosine 200t plus 33.7 degrees volts. Suppose omega is 3000 radians per second. At 3000 radians per second, h of omega evaluated at 3000 is 1 over 1 plus j3, which in polar coordinates 0.31623 at an angle of minus 71.6 degrees. So this is telling us that at this frequency of operation, the input amplitude is going to be multiplied by 0.316, and the phase is going to be shifted by minus 71.6 degrees. So V out sub 2 of t would be what? It would be 0.31623 times 2 times cosine of 3000 t minus 20 degrees minus 71.6 degrees, or 0.63246 cosine of 3000 t minus 91.6 degrees volts. Likewise, if omega is 10 to the 5th radians per second, the last case, now h of omega is equal to what? It's 1 over 1 plus j 100, which in polar coordinates is 0.0099995 at an angle of minus 89.43 degrees. So V out sub 3 of t is going to be what? The input amplitude of 2 is going to get multiplied by 0.009995, and the input angle of plus 15 is going to be adjusted by negative 89.43 degrees, and we end up getting 0.019999 cosine 10 to the 5th t minus 74.43 degrees. So what we see here is by using this general transfer function, we can now calculate the output for a whole bunch of different inputs rather than starting from scratch each time. So the other thing we can do with this transfer function is come up with a frequency response plot, which is going to be a graphical representation of how that circuit operates in the frequency domain. Now the big thing is you cannot plot the transfer function directly. Why? Because h of omega is a complex function. But what you can plot is the magnitude response and the phase response. Remember, both of these functions here are real functions. So you can plot them versus omega. What the magnitude response plot gives us is it shows the gain or the amplification as a function of frequency. And the phase response plot shows us the phase shift, which is related to a time shift as a function of frequency. So if you took our functions from a couple pages ago, if you took this function here and plotted it versus omega, and then if you took this function here and plotted it versus omega, you would get these two plots here. There are different variations of the frequency response plot depending upon what you're looking for. One, which we're going to talk about in this course, is called a Bode plot. It's a slight variation of the standard plots shown here. There's also something called a Nyquist plot, and a third plot called a Nichols plot. Both of these show up in more advanced electrical engineering courses dealing with control theory. So we will not look at the Nyquist plot or the Nichols plot in this course. If you are in electrical engineering and take a course such as EE 380 on linear control systems, you would learn about the Nyquist and Nichols plots. But what we will do in this class is briefly talk about the Bode plot. So what exactly is a Bode plot? Well, Bode plots were invented in the 1930s by Hendrik Wade Bode, and it is pronounced Bode, not Bode. It is a Bode plot. And it is a very conventional way to display frequency response plots. So the independent variable, whether we're talking about the magnitude response or the phase response, is frequency, but it is plotted on a logarithmic scale. If you look on this page here, the frequency is on a linear scale, 1,000, 2,000, 3,000, 4,000, 5,000, etc. In other words, the frequencies are equispaced. In a log scale, we'll show this, we'll jump ahead here, is 10, 100, 1,000, 10,000, 100,000 are equally spaced. This is called a logarithmic scale. Notice the lines themselves. So if that's 10, this is 20, 30, 40, they get closer together, 50, 60, 70, 80, 90, 100. This would be 200, 300, etc. This would be 2,000. This would be 3,000. So as you progress to the right, the frequencies get much, much closer together. So this distance is between 10 and 20 radians per second, but between here and here would be between 40,000 and 50,000 radians per second. So that's the first key thing with Bode plots, is that the frequency is plotted on a logarithmic scale. The dependent variable of the magnitude subplot is the magnitude of the transfer function, also measured on a logarithmic scale, and specifically we do it a decibel scale. So decibels, as we'll review in a page or so, it basically means you take the log base 10 and then multiply it by 20. It takes a bit to get used to using decibels at first, but eventually you can get very familiar with working with decibels, and it's pretty easy to deal with them. The dependent variable of the phase subplot is just the phase angle measured in either degrees or radians, although typically we do it in degrees. So how do you construct a Bode plot? Well, you can use a graphing calculator or a computer to construct it, just like you would a regular frequency response plot, or You will learn in courses such as EE350 how to estimate one manually using standard graphing paper and a straight edge or ruler. So we're not going to talk about that in this course. We're going to focus more on just the concept of the Bode plot. Because the magnitude plot has a y-axis that's going to be measured in decibels, it's important to review what we mean by decibel. So decibels are a mathematical tool that are used to compare ratios that could vary greatly by using logarithms. It's used a lot with powers, for example, and the idea here is if you have a wide dynamic range in powers, doing it on a dB scale makes it easier to see the differences between things that are very small and things that are very large. So when comparing powers, the decibel is the measured power divided by the reference power. Then you take the log base 10 and multiply it by 10 and you get the decibel. So this type of scale is used a lot in audio engineering. You hear about how many dBs a certain sound is. In audio engineering, the reference power is a threshold of hearing, the absolutely smallest sound that you can actually hear. And so dB basically gives us a ratio of the power of the sound we're measuring versus the smallest power that you can possibly hear. dBs also show up, for example, in earthquakes. The Richter scale is a decibel scale as well. In our situation here, we have a slight variation on the decibel equation. First off, we're not measuring ratios of powers, we're measuring ratios of voltages, output voltage over input voltage. Because we're using voltages rather than powers, the dB equation has a 20 out front rather than a 10 out front. The other thing we need to understand is that our reference voltage, as we call it, is nothing more than the magnitude of our input voltage, and then our measured voltage is the magnitude of our output voltage. So the equation we will use for dB is 20 log base 10 of the ratio of output voltage over input voltage. And of course, output voltage over input voltage is what we commonly call gain. At this point, what we want to do is establish a one-to-one relationship between standard gain that we're familiar with and dB gain that we're going to be using a lot of in the coming lectures. So from the equation on the previous page, we see that if you have the standard gain, you take the log base 10 of it, then multiply it by 20 to get the gain in dB. We can then invert that equation to get the second one. If you have the gain in dB, the way to get the standard gain is you divide by 20, then take 10 to that ratio, and that gives us our standard gain. So from these two equations, we can now find these relationships between traditional gain and gain in dB. So a gain of 1, which of course is no amplification or no attenuation at all, in dB, we plug this into here. The log of 1 is 0. So a gain of 1 is the same as a dB gain of 0 dB. So the first thing you need to remember is that 0 dB just means no amplification and no attenuation. This takes a little bit of getting used to because you normally think of 0 as meaning multiplying by 0. But in this case, 0 dB means multiplying by 1. In other words, if you have a circuit with a gain of 0 dB, we're saying that the input transfers to the output with no amplification or no attenuation. Suppose you have a traditional gain of 2. Plugging that into this equation here, the log of 2 is 0.3. 0.3 times 20 is 6. So 6 dB and a gain of 2 mean the same thing. How about 10? Once again, plug it into that equation there. The log of 10 is 1. So a gain of 10 is a dB gain of 20 dB. This is a very important one to remember. 20 dB means a gain of 10. What happens if you plug 100 into that equation? The log of 100 is 2. 20 times 2 is 40. We get 40 dB is the same as a gain of 100. This pattern actually repeats. So 60 dB would be a gain of 1,000. 80 dB would be a gain of 10,000. In fact, what we see is every time you increase the gain by a factor of 10, from 1 to 10 to 100 to 1,000 to 10,000, you increase the dB gain by 20, from 0 to 20 to 40 to 60 to 80. So notice taking a dB turns a multiplicative relationship into an additive relationship. In fact, this is one of the reasons we like using dBs, is it scales things down so that things that have a very large difference in amplitude have a relatively small difference in dB. It just makes it easier to see on a plot. Let's look now at gains that are less than 1. So if you plug in 0.707 into this equation here, you end up getting -3. So the first thing we see is that if your gain is less than 1 in dB, it gives you a negative. So a positive dB means amplification, 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 amplification. 0 dB means no amplification or attenuation. And a negative dB means attenuation. 0.5 plugged into here, you get -6 dB. 0.1 plugged into here, the log of 0.1 is -1, so you get -20 dB. 0.01, you get -40 dB. So a couple things we're seeing here, just like for the positive dB, we see that every time you decrease the regular gain by a factor of 10, you subtract 20 dB from the dB gain. So that means that a gain of 0.001 would be -60 dB, and a gain of 0.0001 would be -80 dB. Every time you go by 20 dB, you go by a factor of 10. The other thing that's interesting is to look at the relationship between the positive and negative dBs. Positive 20 dB is 10, negative 20 dB is 1/10. Positive 40 dB is 100, negative 40 dB is 1/100. So we see that inverses in regular gain are manifested as negatives in dB gain. Finally, what about a gain of 0? In other words, if the input does not show up at the output at all. In this case, V out is 0. You plug in 0 into that. What is the log of 0? The log of 0 is actually -infinity. So the way you represent a gain of 0 in decibels, it's -infinity dB. So a couple of these are probably worth memorizing. You absolutely want to memorize the fact that 0 dB is a gain of 1. You want to memorize the fact that 20 dB is a gain of 10. Then you want to remember the fact that amplifying it by a factor of 10 is the same as adding 20 dB. That gives you the 40, the 60, and 80. Then you probably want to remember that -20 dB is 0.1. Likewise, -40, -60, -80 are 0.01, 0.001, 0.0001. So these are the ones that are most important. The minus 3 dB is a special case that we will look at a little bit later. For now, you don't have to worry too much about it, but we will see this minus 3 dB. This has some significance in filters. So we'll finish up this lecture by looking at the plot of the Bode plot again. So what we see here is that on the x-axis, for both the magnitude plot and the phase plot, we have a logarithmic scale. One of the features of the Bode plot is that the frequency is in a log scale. The other thing we see now is that the y-axis of the magnitude plot is going to be measured in dB. So the way you interpret this, the 0 on top does not mean 0 in the sense that we're used to. This actually means a gain of 1. Likewise, the minus 20 means 0.1, the minus 40 means 0.01, etc. For the phase plot, the y-axis is just your traditional angle in degrees, so there's nothing special there. But in the magnitude plot, you do need to remember that your y-axis is in dBs, so you interpret those numbers differently than you would in a standard frequency plot. Finally, mentioning again, a negative dB does not mean a negative number in the sense that we're used to. What it means is a gain less than 1. So we will pick this up next class and look at Bode plots in more detail and see how we could use them and see what this plot is actually telling us. At this point, we just need to understand that the x-axis is the frequency on a log scale, and the y-axis, at least for the magnitude plot, is also a logarithmic scale in form of the dB. Have a good day.